Thank you very much, and thanks to the organisers and all of you for a fascinating few days. I thought I would just very quickly say BIOS is not a university, we're a research institute. There's about 60 of us spread over Scotland, about half of them are in Edinburgh, and we work on developing methods for application in, across modelling, bioinformatics and statistics, and applied in agriculture, food and environment. So our epidemiology in general is about animals and plants, not humans, although obviously in COVID we did do some work on humans. And then in terms of, so it's just a kind of an appeal to reach out to us if you think we might be useful to you. So in terms of impacts, we have great links with the Scottish Government and various agencies. And also we do have jobs and we like to write proposals with other people. So yeah, that's... and if I put you off in this talk, there's other great people to work with as well in BIOS. So, moving on to the talk, which I forgot to start. I always put my timer here and then I forget to start it, but anyway. So what I want to talk about is how we model contact behaviour and sort of propose a kind of new approach to doing that. At least we think it's new, but you might tell me it's all been done. So I'm going to start off just by talking a bit about contact matrices and the way that contact is modelled in current epidemiology. This is as much for the non-epidemiologists as the epidemiologists, well, probably more for the non-epidemiologists. You've probably seen this already, but so this is a kind of SIR model, so you have susceptible, infected and recovered, and the rate at which you move from being susceptible to infected is proportional to the proportion of individuals that are infected and some contact rate beta. And that is typically how we model contacts between individuals that then lead to disease transmission. So also you can formulate this model as a deterministic model or a stochastic model. The stochastic model is more computation intense, but you can do things like extend it to become non-Markovian, which means it kind of depends on the history more. So for example, the I to R transition could be some distribution with some particular time scale associated with it. And also you can give up on the non-Markovian assumption for exposure and so on, which might relate to environmental exposure and things in particular that we just heard about from Parna. So typically, yeah, the rate of transmission is kind of the contact rate times some probability of transmission. And then, so that's just illustrating some stochastic models. So R0 is the basic reproduction number. If R0 is less than 1, the epidemics typically dies out stochastically in the stochastic case. And if it's bigger than 1, it grows. We hopefully all know that by the end of this week. And then you can also think about, so that was obviously just a single population, well mixed. You can think about that as a network, which is completely connected. So that's on the, whatever side that is to you, it's my right. And then you can also think of, for example, meta populations where you have contacts mediated by some network structure, and then your contact rates depend on which group you're in, which group the infected in, and which group the susceptible's in. And so this is similar to what Katie talked about in her talk on Monday, I think it was. You can also then have a kind of standard kind of network approach to this. And in each case, you can work out R0. And you can think about R0 as being decomposed into two terms, the transmissibility, which is like the probability that you transmit, and then the contact structure, which is the probability that individuals come into contact. And then just to say that from what Katie spoke about, you can have the things that I've just spoken about. You can also then have dynamic networks, but you have to be careful with dynamics because you can't take averages in the wrong place. So you can't just take the average network and think you'll get a good R0 from that. Anyway, none of that is really what I want to say. What I really want to say is that in reality, all these contacts actually arise from things that people want to do anyway. So people don't go around thinking, oh, I think I might have a disease contact today. They go around thinking I need to go to the shops, I need to pick up the kids from school, whatever it is. And those processes are, obviously they're extremely complex processes, and they're driven by lots of potential external drivers like regulation, economics, advertising, various incentives, and also public health, we hope. So these behaviours themselves are what leads to what we think of as disease transmission events, or contacts, which then lead to disease transmission events. And so the contacts that we think about are really driven by these very complex socioeconomics, right? So the slides I showed at the start with, in a way, we do that because we can't cope with this. I suppose what I'm saying in this talk is that we perhaps, although this has been a very successful approximation, we can see some limits in this. So, for example, in COVID, we had sort of the idea of compensatory behaviour, so people getting around restrictions. And so what I want to do is make the case that we should try and relax this assumption and think about some of these underlying drivers that cause people to behave in this way. And I think Parna's talk was actually a good example of that, where people are looking for water and they need to go and get water. They can't just decide they're not going to do that. So what I'm not sure about is whether you're going to like what I'm suggesting. So let's be interested to hear what you think. So what we're proposing is something that I'm calling the contact driver process, where the underlying drivers for this are these kind of socioeconomic factors, but I'm not necessarily saying we should account for all those. So this is a kind of very simplified view nonetheless, but it's kind of one step forward maybe. And so that sits at the center. And then the idea of this approach is that we have something we've called individual drivers. So for a particular behavior, you might have some kind of desire that you want to do it, like go and get some food from the shops. And if you wait long enough, then the idea is that the driver builds up to a point where you actually do something about it. In the sort of general kind of idea, you might first of all think about, okay, which shop am I going to go to? So that kind of then defines what clique you might, or what set of cliques that you might think about. So you might think I might go to Aldi, or I might go to Sainsbury's, whatever. And that will cause me to interact with different people, but I haven't actually done that yet. So then I decide I'm going to interact, so I'm going to go off and do this activity, and then I'm going to be exposed. So in Parna's example, maybe this is I decide which water place I'm going to go to. And when I do this interaction event, it kind of partially satiates this driver, so it kind of reduces my desire to go and do it again immediately. Although you could imagine scenarios where actually it has the opposite effect and I just want to go out again. Say I went out last night, so I want to go out again tonight. And then only then do we potentially get disease transmission happening when we're engaged in these interaction events. Okay, so that's the broad framework. That I've just described. That's just summarizing what I just said, I think. So the key thing is that individual drivers recharge at some rate, which is intrinsic to the person and potentially also linked to some of these system drivers. So a very simple example of this is this model here, where we have an individual. This represents an individual. So an individual has got this driver, which kind of accumulates over time at some rate. And then it switches between behaviour A and B. So it switches between a behaviour that doesn't involve contact and a behaviour that does involve contact. And then it switches back. So it spends a certain amount of time engaging in this behaviour, and then it goes back there. And that is mediated by the driver. So the larger the driver value is, the more likely you are to engage in this behaviour. Okay, and then, so I could just think of this as a model for this behaviour. Might not be a very good model for many behaviours, but anyway. And I could work with this and forget about disease, and I think that's one of the key things we need to bear in mind. But I can also then embed this into some kind of disease dynamic. So this is an SIR dynamic. So these little circles are individuals. When they're like this, they're closed, so they're not they're not able to interact with anything else. They're like at home or something. And in this state, the only disease activity that can happen is that they can progress. If they are infected, they can recover. But over here, when they engage in the contact-inducing behaviour, they then get involved in transmission, so they can transmit to others or they can become infected. So I totally accept there's loads of problems with this, right? So I mean, there's lots of things you could object to about this, but this is kind of a start. You can write a set of deterministic equations down for this, for those that want to see that. So, you know, the behaviours there are the behaviours of people kind of moving between the contact-inducing and the non-contact-inducing behaviour. And as they do that, that impacts their behavioural driver. So, you know, you have a sort of natural rate of increase, and then when you engage in the contact-inducing behaviour, that diminishes your driver. Okay, so in this simple model, what kind of effects does that have? So again, these are kind of preliminary results, but and the colour choice maybe wasn't the best, but the idea here is that you've got some outbreak that's happening, and where there's the vertical dotted line is when some control is introduced. So that control represents some attempt to minimize your engagement with this contact-inducing behavior, but it's not absolute. So it's not like Parna talked about earlier of just cutting the route to the water well. It's kind of saying putting some incentives in place to stop you doing it. And the rationale for this was partly because we were thinking that you know, in some places, although, you know, in the UK, many of us worked at home, but in many places around the world, you couldn't really tell people to stay at home. You could maybe encourage them to go less or to go out less, but it wouldn't be realistic to expect people to stay at home for weeks on end. So in the driver dynamic model, what you find is that if the control is high enough, what you find is that you do get some suppressive effect, but then because you're forcing people to sort of dismiss what they need to do, what they want to do, what the driver is telling them to do, the driver accumulates, and at some point that overcomes whatever barrier you've put in place, this soft barrier that you've put in place, and then you get the secondary outbreak. Whereas in the model without driver dynamics, when you have high level of control, you just see this kind of reduction curve. And so you could sort of say, well, maybe that's a useful thing to try and estimate from data or something. We haven't done that yet. But it also allows you to think about, okay, well, maybe there's other ways that we can intervene. And I guess this is what happened in COVID, where we kind of had furlough, which tried to encourage people to stay at home, for example. But you could imagine other things where you might deliver food. I mean, I guess this has happened in previous times when people have been isolated and their essentials have been brought to them. So that then reduces their need to go out and engage in potentially risky behaviour. And so then you can look at simulations that do the same, and then that mitigate the effect of the driver. So, you know, if you do that enough, you can overcome these issues. Okay, right. Yeah, I thought it was probably worth just mentioning that, you know, that a lot of work that's been done in the past along these lines has been thinking about awareness and how awareness of disease maybe encourages people to stay at home or sort of avoid some behaviour. So you can look at the interaction of those kind of dynamics where the awareness increases with some kind of time average version of the cases, but diminishes in some way. It's a bit like an immunity here. And what you find is that in the dotted lines are the case where there's no driver, and you find in this parameters that I've used here that you get a very strong kind of avoidance, so you kind of suppress the epidemic curve a lot. But if you turn on the driver, then again the same kind of thing happens, and the driver forces people to sort of, you know, there's a competition between fear and other needs. Okay, so that's all very theoretical, and it's something we're trying to develop further. But what I want to show you now is that this kind of relates to something that's kind of more real and has got some data behind it. So we're applying these ideas to modelling disease spread, or diseases that are spread via trade of livestock. So remember, we have this kind of process, or this kind of picture with these different elements. So in this case, we can go through each of these elements and talk about, I'll just talk a bit. I'm not going to show the detail of the model because I don't think I've got time to do that. But I'm just going to talk a little bit about the different drivers or the different elements of that diagram. So the first one is the systems drivers. In this case, the only real system driver that happens universally in these simulations that I'm going to show you is price. So there's a kind of price mechanism to help mediate the trade. And then there might be some other system drivers. So you might introduce some kind of biosecurity controls. And also you might introduce some kind of idea of sharing information, which I'll talk about later, which is mediated by, provides some kind of risk information. Okay, so then the individual drivers in this case are quite simple. So what we're doing is modeling individual farms, and individual farms have got a demand and a supply level. So they've got a demand for a certain number of animals, or they've got a demand for animals, and they've got a supply that they could supply. And that is mediated by these two rates, which are the rate of supply and demand. And those things are directly informed by data. So we have data for Scotland, we have data on every cattle farm, how many animals they bought and sold over a period, and we can use that to parameterize these numbers. Okay. And so these supply and demands increase by these rates, but then they're obviously reduced when you sell animals. So if you sell an animal, the demand goes down. If you buy an animal, your demand goes down. If you supply an animal, your supply goes down. Okay. And then in terms of individual cliques, we have the idea of potential trade partners. So every farm kind of maintains a list of people that it thinks it might trade with. And what we found was that if we didn't have this, we found that the dynamics became very well mixed. So this was a kind of tool that we used to try and prevent complete mixing in the system, in the simulations. And then, you can add and remove people from your supplier list, depending on whether you've traded with them recently and so on. And for example, if you had information on risks of given farms, you could use that to remove those people from your list. And then our interaction events are obviously trade. So when an animal moves from one farm to another, it can potentially spread disease. Shouldn't say that. So the interaction event is the trade. So it's just the movement of one animal from another, and that changes your supply and demand on the buying and selling farms. And then if the animal is diseased, there's a chance that it could infect your farm. So it's a chance that animal brings disease to your farm. Okay. And that was what I was going to say. We had some discussions about this idea of a two-stage process between deciding what, from a suite of activities that you could do, and then actually doing the activity in the abstraction working group. So this is a kind of a picture of what's going on. So this is me. This is my farm. This is my trading list. I can choose at some point that I'm going to buy, I've got a list of traders, a list of people that I could buy animals from, and I can choose to select to buy animals from this farm, and then the animal moves into my farm. Some points worth noting are that, as I say, we've got lots of data on this. So when we're thinking about modelling behaviour, we have an awful lot of information that we can use to parameterize this model. The other interesting thing is that if you look at the number of trades, they're not power law, but they're power law-like. So you have lots of farms that do very little and a few that do an awful lot of trading. which we'll come back to. And then, so the first question is does this work? So when we kind of fit this model to the data, we can then look and see how well the model reproduces other aspects of the data that we didn't use to fit it. And broadly speaking, what I'm telling you is that it works amazingly well. But there is some aspects which don't work so well. So, for example, basically good fit is lying on the 45-degree line. Average batch size kind of is okay, but we could possibly improve that. And then you can then embed a sort of disease dynamic on this. So what we've done here is an SIS model. So every farm is either susceptible, infected, and then after a certain period of time it recovers, unless it's reinfected, obviously. And then we can look at various controls like biosecurity, by which I mean the rate at which you recover. So you do things that help you recover slightly faster, or test and cull, or test animals when you bring them onto the farm, and then do something about that. So if they test positive, you might cull those animals and decide you don't want them. And the other things that you can do, which this model allows you to start thinking about, are things like changing your trading behaviour, or you could do various combinations of all those things. Okay, so is this helpful in any way? So the first thing is, one thing you can do is encourage people to trade in slightly larger batches. So I think at the moment that this is the kind of default, is around on average about 3. And you could think about, if you encourage people to trade in larger batches, then what that does is rewire the network in some way. This top one here kind of shows that there is a penalty for doing this. So when you first introduce these changes, you get a dip in the average flow, but it does recover, depending on how severe that is, it does recover in some relatively small amount of time. And so the system kind of rebalances. And here we're looking at the prevalence of quite a persistent disease, which is on roughly about 50% of all the farms without any intervention. And you can see that there is some payoff. You do get some benefit in reducing this, in increasing the batch size. The other thing I should say is that there was some previous work that was done on this which didn't account for this kind of driver effect, and that shows that incorporating the driver effect actually diminishes this benefit. So it kind of again shows that there's this compensatory kind of behaviour happening in this model. You can also look at combinations of different interventions, and what we find is that when you combine trade with other interventions, that you kind of get a synergistic effect, so you get more than the additive effect. So that's shown over there, where you can see that biosecurity, test and trade all have relatively small benefits, but when you combine them, you get more than the sum of the parts. I think probably the most interesting thing, and maybe this relates to some of the equity conversations we've been having, is that because you have this kind of power law structure in this situation, you can actually target controls on the larger farms and still get quite a large benefit. So you can see that you get a sizable benefit if you target the 25% of farms, for example. And these curves also show this sort of synergistic effect. Right, so another thing you can do is provide information. So when animals move, you can test them and then put that information in the public domain, and then people that are buying animals can look at that and decide whether they want to buy from the farms that have provided those animals. There's loads of issues with that, and I've had lots of conversations with farmers and farming representatives, and some of them love it and some of them hate it as an idea. But the first thing to say is that in this scenario, the same disease scenario that I showed before, if you test the batches that are coming onto farms and reject those animals, so cull them, you can potentially get a huge benefit from this. And if you don't cull them, you can still get some benefit, but it's less. But it does show that there is a benefit of purely the information being provided, and people acting on it, obviously. And then similarly, you can look at heterogeneity to kind of focus on a smaller number of farms. So you can force only the largest selling farms to provide information on, you can provide information from only the largest set of farms that are selling animals. And that, again, similarly, you can get quite large effects from a relatively small fraction of them. Okay, so I think I'm almost done. So I think that the sort of key insights are that, disease control is complicated by the fact that disease is caused by things that people want to do anyway, effectively. You can impose severe restrictions. So in the cattle trading cage, you can have movement standstills, but that obviously brings the whole industry to a standstill, and is very costly and can only be done for a period of time. So a sort of systems kind of approach would ask questions like, can we modify the system in a way that reduces the impact of disease when it comes, so reduces R naught effectively. I should have said you can do R naught calculations for these models that I spoke about. And also the idea of focusing on contact structure might actually allow you to tackle multiple sets of pathogens at once, which is a particular, well, I guess it's an issue in human epidemiology, but certainly an issue in agriculture where there's a lot of pathogens that are, emerging for various reasons, climate change and also global trade. So what I would say is that this is not the final word on this by any means, but I think this is a sort of way of thinking about things that is worth pursuing. And maybe that, as well as these benefits, it's possible that we could do things that would actually make things worse, and there have been some examples of that, possibly, in the past. So we can potentially use these approaches to mitigate against those issues. Okay, and then just finally, very quickly, I originally wanted to do, I had a lot of ambitions for this week, which, I didn't quite make. But early on in the week, I had to play around with this equation, which is called the swing equation, which is to do with the sorts of things that Chris was talking about earlier. I am completely out of my comfort zone here. But essentially, it treats a series of nodes on a power grid as kind of oscillators, and it thinks about how the periodicity of the oscillator at each node varies compared to the mean, I believe, and it allows you to treat those as a bunch of springs essentially. And I think Chris mentioned in his talk that there was a kind of like swings in frequency. Anyway, so you essentially get a network equation where each node is represented by its inertia, its damping, whether it supplies or takes energy from the system, and the coupling with other nodes. And so in my very naive way of trying to sort of make a bridge between these two areas, I was thinking that the supply and demand represents this kind of supply and demand of power into this. We've got a highly heterogeneous population, in this case coupled by a physical process, not an epidemiological process. The nodes themselves can adopt many dynamic behaviors that we could think about modeling. And in terms of the energy transmission, renewables have different power profiles over time compared to traditional generators. They also have different sort of characteristics in terms of the inertia and damping. And then there's things like battery storage and consumer behavior that we could try to model. I'm not quite sure what word that is. But anyway, that's what happens. That's what happens when you do a slide just after lunch. So yeah, that's me. Thank you very much for your attention.